Hi everyone, my name is Sunil Kumar and I'm going to talk about my work on critically sampled wavelet filterbank on graphs. So the problem that motivates our work is big data. So everyone is already hailing this age as age of big data. Here are some numbers, and there are more that we keep on hearing about the size of this big data. And therefore we need a new generation of scientific computing tools to manage, visualize, and analyze the data flow. So graphs provide a flexible model to represent many of these data sets, such as high-dimensional data, transport networks, social networks, network control, and many other problems. Algebraically, we represent a graph as G is equal to VEW, where V are the nodes, E are the links between the nodes, and Ws are the weights on the link which represent similarities or differences, etc. The nodes in the graph produce data, which can be represented as a scalar sample, F1, F2, F3, etc., and combined together, the set of these samples are called graph signals. So my research problem is that once we have this representation of data set, how do we analyze, compress, and store these graph signals? And the solution that we propose is wavelet filterbank on graphs. So why wavelets? As I said, that the size of these graph data sets are massive. In fact, in many situations, they have costly data exchanges. So the solution that we provide is to, instead of working on the original graph, we provide a successive coarse approximation of the graphs, like from left side to right, and operate on the smaller graphs with fewer nodes, and do all the processing on the smaller graphs. And after the processing, interpolate the data back to the original domain. And we find that wavelet approximation in digital signal processing domain does the similar thing. So what are wavelet transform? Well, briefly, they are a popular tool in compression, analysis, and storage. The general idea is that instead of storing this big image, we decompose it into 4 subband images of smaller size, where LL is an approximation, a coarse approximation of the original image, and other 3 channels are just the details which are not covered in the LL band. And we can work on the smaller image. But we can do further decomposition. We can even find a smaller image to the size which is convenient for us for processing, and then we can interpolate the data back on the original domain. The limitations are that these are designed only for uniformly sampled signals. So this is the way I have extended the wavelets from images to graph. I first of all view an image as a graph with pixels as nodes, for example, figure A, and then I extend it to more general situations such as irregular grids and to completely arbitrary graphs. The problem that we face here is that unlike the regular graphs that we find in image, we don't have any obvious orientations to filter and downsample. So my key contributions are that I have defined downsampling of sampling operation on graphs, and using this concept, I have designed critically sampled 2-channel wavelet filterbank on graphs. So some examples for images, when we try our graph QML filterbank as compared to the standard, we find that they are less detail produced. That means most of the energy goes into the LL band. And this is because with the graph-based filterbank, we have flexibility to have more orientations to filter and downsample. As a result, when we try to interpolate the data back in the original domain, with same number of coefficients, we get better picture than the standard filterbank. So that's one example. Other example is, for example, analyzing the graphs, so Minnesota traffic graph. Here, the nodes represent stations, and the links represent the roads connecting them. So the middle area is, for example, Minneapolis. And let's say we have this signal which represents high traffic, low traffic scenario. So downtown has a lot of traffic. When we apply our graph-based filterbank, we see clearly that the one of the channel is an approximation of the original signal, and the other ones are high wherever the traffic situation is changing. So we get wavelet-like effect with them. And this is the power that we can interpolate the data back on the original graph domain, and we see the same effect. So we are working on a lot more problem. In case you want to know, you can talk to me later on. And here's our website link. Thank you very much, and questions.